Hi, welcome to this video on binary dependent variables. This is in preparation for the lab tomorrow, and actually all I want to do today is to give you a bit of an overview of the model that you will be using tomorrow in the lab. So we're going to be switching from continuous random variables, which has been the focus so far, to binary dependent variables. And an excellent example of one of those variables is actually the decision to participate in an election or to abstain in that election. So Wolfinger and Rosenstone in a seminal book actually tried to model out why some people vote and other people abstain. And so we have here an outcome variable that has just two states, vote or abstain. So there's nothing continuous about this, but we can still actually assign numeric values to these outcomes of vote and abstain. A common way to do that, for example, would be to define a random variable y for some individual I, which would take on the value 1 if that person voted and 0 if that person abstained. And that we could go on our merry way trying to analyze that dependent variable. But what we need to be cognizant of is that the actual coding of the dependent variable here is actually very arbitrary. The values here are really only there to distinguish voters from abstainers. So everyone who votes gets one value, everyone who abstains gets a different value, but what those values really are, that's actually completely arbitrary. So 1 and 0 is just one option. We could actually also have used 1,000 for voting and minus 1,000,000 for abstention. Would have been equally valid. So the problem we run into here is that we really should not be predicting the values of the dependent variable. We really should actually be focusing on class probabilities. So what is the probability of voting? And of course, assuming that voting and abstention are the only two alternatives that a voter or a citizen had at his or her disposal, and they're mutually exclusive, then of course the probability of abstention is just equal to 1 minus the probability of voting. So what this all suggests is that we should not be using a regression model because that is focused on the values of the outcome variable. We need a model that is about the probabilities. Now, you may have heard of people using a linear probability model. So that is one of those models that actually effectively ends up modeling a probability. Because if y is a binary dependent variable, say with values 0 and 1, then mathematically the expectation of y is equal to the probability that y equals 1, and we could say that that is equal to the probability pi. And of course, in a regression model, the conditional expectation function of y given x would be equal to x transpose beta, so we could just equate that then to this pi that is anyways the mean of a binary dependent variable that takes on values 0 and 1. And that is the linear probability model. Linear probability model says, okay, the predicted probability or the probability pi I of someone voting, say, is equal to some linear function of the predictors in the vector x. But this model has a couple of disadvantages. One is that it has built-in heteroscedasticity because The variance of a binary dependent variable is pi times 1 minus pi. But here the variance is actually a function of x, and so we're talking of pi sub I being a function of x sub I, and the variance is equal to pi I times 1 minus pi I. So we also have here very typically out of bound predictions. That is to say, there is absolutely nothing in this linear probability model that actually prevents us getting predicted probabilities that are negative or greater than 1. But obviously, the rules of probability theory require that probabilities are bounded by 0 and 1. So these are nonsensical predictions. They arise because ordinary least squares doesn't know that what it effectively is doing is estimating a linear probability model. It thinks it's estimating a regression model just like any other regression model, and that it so happens that actually the mu I should be equal to pi I. Well, it is blissfully unaware of that. And the third limitation of this linear probability model is that there is a very restrictive functional form, and that is often unrealistic. The idea is, like in any other regression model, that a unit increase in x would always produce the same change in pi. But that doesn't seem to make a lot of sense. Say that an article costs 50 cents and someone has just 1 cent, then I can give them a cent, but the probability of them being able to purchase that item is still going to be more or less 0. On the other hand, if they have 49 cents and I give them the same cent, suddenly they have the ability to purchase the item. So the effect of x in that example isn't constant but fluctuates. And that is often the case actually with these kinds of variables. So we want to actually do something about this linear probability model, and we want to actually get an alternative that is homoscedastic, that has predicted probabilities that are always between 0 and 1. Technically, as we will see actually in a moment, that 0 or 1 is not really included. But what we certainly are accomplishing is that we don't get negative predicted probabilities or predicted probabilities exceeding 1. And we're also getting rid of this problem of the constant effect of x, and we do that here by using an S-shaped functional form. So that brings us to Logit and probit. So the Logit and probit models are basically transformations of the linear predictor x transpose beta. So what we're doing is we're saying pi I is not equal to x transpose beta, but pi I is equal to some transformation capital F of xi transpose beta. And what that transformation F is, that is actually the link function. And we have many choices in terms of link functions. Historically, the first link function that was proposed is actually the probit link function. That's the one that actually you see here. And that's the one that uses the standard normal cumulative distribution function as capital F. This is a very complex function to work with. There is no closed form for that capital phi, that standard normal CDF. We typically express this as capital phi. There's no closed form for it. And that means historically, actually, even though the probit model is older, the method of Logits, as it was sometimes called, actually dominated for a long period in statistics. And here the capital F is taking the form of e raised to the power of the linear predictor divided by 1 plus e raised to the power of the linear predictor. If you look at these Logit and probit curves, they look very similar, but actually for our purposes, actually two things stand immediately out. If we look at the horizontal scale, the linear predictor scale, then that is unbounded. Even though I've just shown it here between -5 and 5, it goes from minus infinity to positive infinity. You see immediately that the vertical axis is bounded between 0 and 1. And you also see that the relationship between the Logit and probit, between the predicted probability and the linear predictor in the Logit and probit curves is S-shaped. Yeah, the Logit model has slightly more probability in the tails than the probit model, but those are typically very trivial differences when we start thinking about the predicted effects in those models. What you don't see here, but that is also working in the background, is that we're using standard normal CDFs or standard logistic CDFs. The standard in there actually means that we're actually imposing homoscedasticity. Now, you might say, well, this is all a wonderful trick, and yeah, so all you've done is you've basically replaced the linear probability model with a function f over the linear probability model. And in one sense, that's actually true, but we can actually come up with a behavioral rationale for these models as well. And that's what I would like to do next. So imagine that we're going back to this participation example. Do you vote or do you not vote in an election? We record that as a 0-1 variable, say. 1 if you voted, 0 if you did not. But we might actually think of that 0-1 variable that we measured as a very crude reflection of a continuous latent variable, call it y star, that measures a person's inclination to vote. So you could imagine this y star being a continuum going from minus infinity, where you could say this is a person who is at that point who has absolutely no inclination to vote, to positive infinity, where you could say, well, some pretty stark forces of the universe have to stop someone from participating. Now we postulate a linear model for the latent variable, the way we would do that in a linear regression analysis. So y star, now a small y because it's the realized value for some individual I, is equal to xi transpose beta plus epsilon I. And that's basically a normal regression model, but with the somewhat nasty detail that the left-hand side is unobserved. Well, normally we observe everything except for the error term and the beta, but here the whole left-hand side is actually unobserved. The first thing that implies is that when we want to estimate that equation that I just threw up there, that we need to connect y star to y, because that's what we actually observe. We don't observe y star, we observe y. And we're going to make the following assumption. We are going to assume that a person participates, that is y, capital Y equals 1, if and only if y star is non-negative. So we write that as an indicator function. Capital YI equals 1 parentheses yi star greater equals 0. So we can also say, well, actually, if we want to write that probabilistically, then pi I, which is the probability that yi equals 1, is equal to the probability that yi star is greater equals 0. And since we just saw a formula for yi star, we can say, well, pi I equals the probability that xi is equal to the probability that xi transpose beta plus epsilon I is greater equals 0. And rearranging terms, that is the probability that epsilon I is greater equal minus xi transpose beta. This point we're actually stuck because now we have to really start making assumptions about the distributions of these errors epsilon, so that we can actually analyze what happens on the right hand side. So we're going to set a distribution, first of all, where the variance of epsilon is fixed. We're going to impose homoscedasticity. We need that assumption because we need to fix the scale of y star, and if we don't fix the scale of y star, we can't fix the scale of beta. Now the third assumption we're going to make is that epsilon follows a symmetrical distribution. And under that assumption, the probability that epsilon is greater equal minus xi transpose beta is identical to the probability that epsilon I is less or equal xi transpose beta. You see that actually reflected in a very simple uniform distribution, which I've drawn here from -2 to +2, and then I've indicated the probability that x is greater equal -1 as this blue area. But if I instead had calculated the probability that x is less or equal 1, I would have gotten a blue area that is exactly as large as what you see in the top plot. Now, if you look at this last term, it's nothing but the cumulative probability, capital F, evaluated at xi transpose beta. And the assumptions that we then make is that one capital version of capital F is the standard logistic distribution, where the variance of epsilon happens to be set equal to pi squared over 3, with pi being the mathematical constant pi, not the probability pi. For the probit, we pick a standard normal distribution for capital F, and there the variance of epsilon is equal to 1. Since these variances are different, actually the scale on which the coefficients are measured for the Logit and the probit model respectively is also different. And so that is one reason why we don't want to really pay too much attention to these coefficients themselves. They don't mean a great deal by themselves. And we have to actually do some additional work, which you will do in the lab tomorrow, to understand what the effect of predictors is. The other reason is, of course, the fact that the relationship between the linear predictor and the probability of voting is not a straight line. It has this S-shaped nature, which means that that relationship varies. These assumptions are really quite important. That's where I want to end this video. Violations of indicator functions, or violations on the idea that we set as our threshold 0, that's not so critical, because if such violations exist, they will be absorbed into the constant. The other assumption, do we do a logit or a probit? That is generally trivial. But the homoscedasticity assumption can be problematic, and using a symmetrical distribution can also be problematic. So you need to think about whether those choices make sense. Thanks for watching.